We can hear you, yes.
Excellent. So, thank you for giving us this great opportunity to present the system we have developed at Perspectiva Solutions. This system we named Huris, and it's actually devoted to preventive maintenance of laser systems using AI. Our company is located in Poland. We were set up in 2012. We are present in a number of photonics organizations across Europe, and our daily work is concentrated on a few pillars. First of all, we are a contract production company, so we do produce various machines, electronic devices, photonic devices, and cable harnesses on the contractual basis for our clients. However, we have one strategic pillar which is related to diagnostics of the laser beam. Since a few years now, we were on the market with our beam profilers, and now we extended this offer to address very specific market problem, which is related to long downtimes of the laser systems. So you might know that when the laser gets broken, it takes really long time to get that repaired. I'm not speaking now about the situations where people or maintenance companies just do the swap of the one laser to the other laser, but I'm talking about the situation when you want to repair it. And this time can be very long. From the market research we did, it was anything between 2 to 4 weeks typically. So we wanted to shorten this downtime, to increase the lasers availability, and the method how we want to do that is through predictive or preventive maintenance. So the value proposition we are bringing to our clients, to the market, is comprising few critical components. First of all, it's automation. So first of all, we have decided to make the detection of the artifacts in the beam in a fully automatic way. So if you work with laser, you know that beam characterization has been there for quite a while, but the assessment of the beam quality has been always done by a man, which limited the use of this technology. And also the additional aspect we wanted to address is long-term monitoring in also automatic way. So if you used to characterize the beam, you know that most of the time people just do a snapshot. You see what you see now, but you don't get really the information what has been going on with the laser over recent weeks or months. We want to change that. Also, if you look from the perspective of the maintenance companies, they really need a tool to monitor the lasers remotely. The business model is to have very few sites from which they support their clients. The effect is that they have to travel a lot, and this traveling makes things even worse in terms of the availability of their service. Of course, if you are a laser company, then your concern would be, how do I implement it on large scale? So our system that we've built is scalable and applicable in the large scale. It's been done by people who are always dealing in the professional careers, always dealing with the large or big data. So they are very used to this sort of problems, and they applied state of the art methods in our systems as well. I would like to mention that, of course, the obvious target for us is science. Sorry, the industrial applications, but the science has been always important for us as well. So we focused also on this sector, and we are very open also for this kind of applications. Our technology is proprietary. It's protected by a patent application. So I think it's been quite unique. So what about the parameters? Well, if you are a technical person, you will immediately ask, what do we monitor? What do we watch for you? First of all, the key data, the basic information is the beam profile. So the 3D map of the laser intensity, in space. Then we monitor also the power. We monitor also the parameters in the time domain, so beam pointing stability, and of course trends in all above all above parameters. Of course, these parameters are kind of generic. I didn't name them very specifically, but I didn't want to consume too much of the time here. I would be very happy to continue this discussion, but for the technical people, probably this gives enough of kind of initial information. Then I would like to present a few examples of what can we detect. So these are classes, speaking the language of AI guys. These classes define what essentially can happen to the laser beam. And in the laser beam, you can have diffraction. You can have linear diffraction. You can have diffraction on the rounded edge. You can have, beam which is affected by rough surface. You can have spherical, various kinds of diffractions on multiple structures, and also evergreen dust. So these five classes of defects are being detected by our AI system. So how did we approach the training process? First of all, we did define the classes, the five classes I just mentioned a slide ago. Then we generated data sets. As you might know, training AI is a tricky thing because you need to have lots of data to make it working well. Then we did some pre-training experiment using various neural networks to test their performance. We benchmarked them to check which is most efficient, and we then performed full-scale training to basically do their work. Another step was to validate the algorithms using experimental data, and then we started playing, to see how much does it withstand of various kinds of situations from life. So we started adding the disturbances, for example, noise, and then we repeated the training and validation cycle. Here I'm showing the learning curves. On the upper graphs, you can see how the accuracy increased with epochs, so various sets of the data, training data. And then on the bottom, you can see the loss function. Loss function essentially tells you how much of error do you make when you are evaluating your image using AI. For each class, we used roughly 50,000 beam profiles, beam images to train. Here there is brief information how the noise impacts the accuracy of AI that we've built. We tested three types of the noise: Gauss, Poisson, and speckle. As you can see that essentially the noise didn't affect the accuracy of AI algorithms too much. There are other factors that affect them, and this is more or less a discovery that we've made, but not the noise, for example. One of the key aspects is the problem of specificity. Here we are showing, just for reference, the architecture of the neural networks that we've developed for those of you who are kind of AI oriented, and you can see the results here. This graph essentially is representation of the classes, how specific they are, in the meaning that essentially if you have these various colors of dots separated from one another, this means that the AI algorithms are capable of being very much successful, so to say, in distinguishing these two types of classes, these two types of defects, as represented by some example two colors. Here we are showing some real life examples of testing using real beams. In the left two columns, we are showing them in color and grayscale. Grayscale sometimes gives a bit better impression what kind of defect do we have there. Then top one means the probability of detecting the right defect, and the top one class is the kind of defect that we have detected. So as you can see, the accuracy is very high. I want to stress this because if you want to build a platform which works fully automatic, then you have to be pretty much sure that whatever the algorithms tell you, they are true positives. So they are giving you the right information about your beam quality. I mentioned information about the long-term monitoring. So the AI algorithms, they were embedded on the web application because essentially the heart, the core of the system is the web application that gathers information about all your lasers, all your metrology, and you can observe that in the web browser, and you can do it remotely and also in the real time. Well, and of course, we have asked to all of you who are present on this presentation. First of all, we are very much open to talk to all partners, potential partners who would like to use our system in the lasers. Specifically, we mean here industrial companies who would like to embed our system into their products. But also we are very happy to work with science. So if that's something interesting for you, if you have extended infrastructure of your laser systems over various floors and big buildings, and you want to monitor your laser remotely from your desk, then we could probably help you. And essentially that's it. I would like to kindly ask you to make a quick snapshot of this slide. If you would like to follow up with me or with my team, and then we would be very happy to hear from you. And finally, we would like to acknowledge the support from the National Center of Research and Development in Poland for the help, financial help in our project through the European funds. Thank you very much. I'll be very happy to answer your questions.
Thank you very much, Christoph. Excellent presentation. Yes, so we're now going to hold a short Q&A session. So if you have any questions for Christoph or any of the speakers, please do drop them in into the question box. Maybe Christoph, we could start with you since you were last to speak. I was asking about, does it matter about the type of laser? I mean, ultra-fast lasers or high-power lasers, does it matter what type of laser you can use this monitoring system for?
Essentially, it does not. The platform is very much universal. we just need to get the beam footprint to have that as an input information for the algorithms to analyze. Of course, before we send the images to the cloud, they have to be somehow, prepared or pre-processed. But essentially, if the detector can detect the wavelength, specific wavelength of the source, then we can work with it.
Nice. Okay. Have you ever thought about or people thought about using it to control the beam at all, like a closed feedback loop? Is that possible or not really advisable?
It is. It is actually. This is also in our patent. So this is something. Of course, we will be offering very shortly, though we are not yet presenting it.
Not quite ready. Okay, but something for the future.
Soon, future. Yeah.